Yeah, okay, so let's go ahead and get started. So before we start, we'd like to acknowledge the current state of the world. We are obviously in the midst of a global pandemic that has resulted in untold hardships, and we thank people for joining us in spite of that. Also, in light of the recent protests, we've had to reflect on how we contribute to the systemic racism that's in the US. As researchers, it can be easy for us to forget that our work does have real-world impact. Computer vision research has been deployed by the military and the police, and our work is being used to oppress people of color. We have to acknowledge this, and we have to do better. So with that said, let's go ahead and get started with introductions of panelists. So quick 2-sentence introductions for everybody. Let's go alphabetically by first name. So we'll start with, Alison and Alex are so close, but I think Alex wins. All right, Alex, we're gonna start with you.
All right. Hi, everyone. My name is Alex Schwing. I'm an assistant professor at UAUC in Urbana-Champaign, and thanks a lot for having me on this panel. Very excited to participate here.
Alison?
Okay. I'm Alison Gopnik. I'm a professor of psychology at the University of California, Berkeley, actually, as well as philosophy, and also a member of BEAR, which is the Berkeley Artificial Intelligence Research Center. And I'm very pleased to be part of this.
Thank you. I think next is Dieter.
Hi, I'm Dieter Fox. I'm professor at University of Washington, Allen School of Computer Science and Engineering, and also leading a robotics research lab for NVIDIA here in Seattle.
Yeah, thank you. Then Deepak.
Hi everyone, I'm Deepak Pathak. I'm currently a researcher at Facebook AI Research, and I'll be starting as assistant professor at Carnegie Mellon University in this fall. I'm very pleased to be part of the panel. Thank you.
Then Franzi.
Hi, I'm Franziska Meier. I'm a research scientist at Facebook AI Research. My research interests are at robotics and machine learning, and I'm also very happy to be part of this panel.
Let's see, there are so many people to keep track of. Oh, Heidi, I completely skipped you. Sorry about that.
That's okay. My name is Heidi Hysell. I'm the founder of a company called Alpha Drive. We work with the Carla team and basically provide tools and data around autonomous driving right now as our first sector, but looking at expanding that.
Thank you. Then Judy.
Hi everyone, I'm Judy Hoffman. I'm an assistant professor at Georgia Tech in the College of Computing, and thank you to the organizers for inviting me to be on this panel.
Then let's go to Linda. I'm just reading people off how they show up in my list now.
Okay, hi, I'm Linda Smith. I'm a developmental psychologist at Indiana University, and I study how babies break into language, and particularly the visual side of it.
Then to Sonia.
Hey, I'm Sonia Chernova. I'm faculty at Georgia Tech in College of Computing as well as ECE. And I'm currently on sabbatical at Facebook AI Research as well. And my work is on robot learning, at the intersection of robot learning and human-robot interactions. I'm really interested in how do robots operate in human environments, and lately I've been doing a lot of work on semantic reasoning.
Then Piotr.
Yes. Hello, I'm Piotr Mirowski. I'm a staff research scientist at DeepMind in London. I'm interested in navigation, learning from real-world data, among others, and I'm very grateful to be part of this panel. Thank you.
Okay, so looking at the poll, let's go ahead and get started. So the top question currently on the poll is, how do humans decide to interact with objects? And can we leverage these techniques in an algorithmic approach? So does anybody want to get started on that?
Well, I could say something about what we know about young children. One of the things that we know is that literally from the time they're extremely small, one of the first things that babies do is to interact with the world. My joke about this is, there are scientists in the crib who are experimenting, except we call it getting into everything. And really, quite recently, over the past 10 or 15 years, we've discovered that at least by the time they're toddlers, it isn't just that they're interacting with the world randomly, they're actually performing interventions that seem to be designed to give them information about the world, and particularly about the causal structure of the world. So it isn't just that they're going around and acting randomly, they're actually doing things that are going to give them some knowledge about how the world works. And in the experiments I talked about in my talk, we showed that in fact, children are better at doing that than adults. So children are more likely to be willing to sacrifice reward, for instance, in order to make an intervention that will give them the information that they need about how the world works. And I think the big interesting challenge now, which is also a challenge for robotics, is there's some interesting mix of intentional actions that are designed to get specific kinds of information, for example, versus just sort of random stochastic action. And when we look at the children, we seem to be see both of those things. So we see a certain amount of just random variability, but it's not completely random. We also see that it seems to be designed to get information from the world that's relevant to the structural problems that the children are trying to solve. And I think an interesting question for roboticists, for example, is how could we formally put together those two pieces? The piece that's about being able to do some stochastic wandering, which helps to solve the fact that a kind of the computational demands of something like actually trying to do active learning, where you're figuring out, here's the sequences of actions I could take and here's the information I could get. That's very computationally demanding. So how's that balanced against just introducing some noise or stochasticity into the exploration, which will give you some other kinds of advantages? So it's some combination of directed exploration that is oriented towards extracting particular kinds of information, and again, with babies and children, random wandering around. And the combination of those two things seems to enable children to learn very quickly in the context of their active exploration.
I see a hand from Linda.
Sure. I just want to, this is maybe perhaps more certainly relevant for roboticists, but the way physical beings enter into the world is through our bodies. And quite interestingly, in the first 2 years of life, those bodies change dramatically. And how they interact with the world changes dramatically, creating really a curriculum of kind of ordered experiences of the physical world. And I think it's a very useful thing for us to think about what that might do.
And to Dieter?
Yeah, so from a robotics perspective, of course, there's a lot of interesting work also on curiosity-driven exploration, right? Or active learning, active investigation of environments. My feeling is that one key limitations we have so far is kind of having really access to the general representations of these kind of manipulation scenes that we can use, right? So we're either using very explicit representations where we have object models over which we can reason and the robot manipulate how it's going to interact with these objects. But I think we need to go beyond these and really learn very general, broad representations of these 3D scenes and interactions. I mean, you see the beginning of that coming up, of course, in computer vision with the recent successes in contrastive learning. But I think in robotics with the much more complex sceneries, we're kind of just still at the beginning. We see some success stories, but it's really early.
Sonia?
Thanks. I completely agree with Dieter that we're very much at the beginning. I'm really interested about the ongoing work and kind of semantic grasping, for example, and I think the robotics community is starting to incrementally look at context, for example, right? What is it about the object, the task, the scene that should influence how someone would grasp? But unlike other areas, I think this is one where we haven't had as much data, like we haven't had large data sets. And as we all know, data drives a lot of research. And anytime you have to collect data from actual people, you know, that's obviously a lot harder. But I think that's an interesting thing to think about in the future is how do we obtain richer data sets that really look at the human aspect of object interaction and help robots become more capable.
Deepak?
Hi. Bringing back to the Alison point of human versus AI kind of direction, I think one important point to also bring out is that most of our current systems in machine learning, whether robotics or vision or any other domain, are kind of task specific, like we train them for a particular task. In contrast, what humans do seems to be more task agnostic or general, like building general priors, which can then later be adapted. And so one question to think about might be like, what does it even mean to set up such an environment for robots? Like, what do we do about safety? What do we do about other constraints? How do we evaluate such a system? And the Sonia's point about data becomes more extreme in this scenario, because now it's already very hard to get data for one task if you're trying to be general and task agnostic. So like, how do you collect your data? Maybe finding things like agent collecting their own data could be more interesting in that kind of setups.
Didn't see who raised their hand first. Dieter, do you have something to say?
That's still the old race. So do I unraise?
Okay.
Or do you unraise? Oh, I lower hand. Sorry, forgot that.
No problem. Linda, do you have something? I see a hand from you.
I wanted to just bolster Deepak's statement. I think that learners are sort of in some ways in the world performing or solving multiple over-layered tasks at all at the same time in the very task-specific way in which AI is organized troublesome. I had an interesting discussion. I'll just say this, I think it's a funny example where we were talking about, actually this was Jim Ray, we were talking about learning 3D object representations from the children's interactions with objects. And he's looking at the videos from the head cameras and he's saying, geez, do you think they're exploring the three-dimensional space and the geometry? And I had to say, no, I think he's trying to get the elephant in the truck. Do you know? But he is exploring it, do you know what I mean? But it's not this driven to explore, you know what I mean? They're doing many things at the same time.
Well, I think we do have some evidence, at least with older children, that they are exploring in ways that enable them to get the kinds of information that they need. So it isn't just that what they're doing is goal-directed. And again, as I say, in these new experiments, they're actually foregoing goal-directed advantage and reward in order to be able to get information, even information that's relevant to a very abstract feature of how the system works. But I do think it's worth saying, this is also echoing Deepak and echoing some of the previous comments, that there's this really interesting kind of bootstrapping interaction going on between being able to figure out representations of how the world works, whether those are object representations, causal representations, and actually doing the exploration. So it seems very plausible that what happens is there's this kind of bootstrapping where the children are seeing what's going on in the world, and simultaneously, this by the way is something that's very reminiscent of Deepak and Pulkit Agarwal's curiosity module. They're simultaneously trying to build an abstract model that lets them make the right kinds of predictions about what's going on in the environment, and also exploring the environment. And as they use their models to explore the environment, they're revising the model, and then the model is enabling them to explore in ways that are different from the ways that they would have explored before. So I think that kind of back and forth bootstrapping is something that you could imagine having in a robotic system. And again, something like the curiosity module is a nice example of that, where simultaneously you're building a model of the environment and then actually using the model of the environment to guide what your exploration should be. And I'll just say, Linda mentioned this in passing, but it's worth mentioning that in fact in Linda's lab and in other labs, there are now some really beautiful data sets of things like what babies see from a head cam recording, so that they can go out. We actually know now what's the data to a remarkable extent, we actually know something about what the data is that is going into the baby's minds in the first couple of years of life or later on. And I think it would be very exciting to use those data sets to try to train AI systems. And then the last thing to say is something that we've been starting to do in our lab. This is again, Eliza Kosoy, who was involved in the work that I was talking about in my talk, is starting to use VR. Because VR is a really nice example where what we can do is actually control the information that, say, a human or a child is receiving, and then we can actually use exactly the same information with an AI algorithm. So we can directly compare, here's the data that the human is getting, here are the actions that they're taking, and we can directly compare that with an AI with in exactly the same kind of VR environment. And we're starting to do that in some work with Corey Lynch and Pierre Sermonet, where they've been training robots with human play behavior. And one of the things that we're planning to do once we get our human subjects research back on track is to try to look at children's play in a VR environment and then see what it would be like if you were training a robot on that kind of play versus the adult play. So I think the VR environments are really interesting. They also give us a chance to see what learning looks like in situations that violate our everyday physics, for example. And we don't know yet whether when you see something that violates everyday physics, do you just sort of seize up? Do you try to interpret it in terms of everyday physics? Or can you actually discover regularities that are different from the regularities of everyday physics? Just some methodological things, the wonderful headcam data of the sort that Linda has collected, and then being able to use some of these VR interfaces. Those are both, I think those are both interesting ways that we could get more relevant data.
Let's go to Alex. I see a hand from him.
Yeah, thanks. Actually, maybe that is more of a question than a comment to the original question. But when we train those reinforcement learning algorithms, right, we often in our systems, we design the rewards ourselves, or we have particular goals in mind that we want those algorithms to pursue. And I'm kind of curious, and I guess maybe that is also a question for Alison and Linda. How do kids do that? They explore the world for a while, and eventually they lose interest and pursue an entirely different goal, which at least to me is seemingly unrelated to what the child has been up to before. So what are these internal reward structures, and how are they developing? I think that is one of the questions that at least I have very little understanding of how is that evolving. Maybe we could shed some light on that question too.
Okay, let's
say a bit about this.
Alison or Linda.
Again, in the context of this curiosity-based reward, I think there's a lot of excitement now about the idea of thinking of, and there's been work for a while by people like Pierre Audouet, for example, about the idea of thinking of curiosity as a reward system on its own. So the problem is trying to figure out again what the metric is for that kind of reward. So one thing could be simple novelty, but what children are doing seems to go beyond just simple novelty, and simply trying to get to something that's novel is not necessarily going to give you the kind of information that you want. Deepak and Pulkit and our group has been talking about the problem of the television screen. So another thing you could do is use some kind of entropy measure. So see if you're attracted to something that's unpredictable. And again, in terms of what you were just saying, of course, when you spend a lot of time doing something, then it's not as unpredictable or novel as it was before, and you turn to something else. But the problem is, how do you avoid the problem that if you then just see random noise, you're captivated by the random noise, because that's always going to be unpredictable. And Deepak and Pulkit have some ways of trying to deal with that by thinking about the kind of actions that you can take, whether or not the information that you're doing is relevant to the specific actions that you've taken. So I think that's another way that you could sort of try to formulate the reward. There's also some very interesting work in RL itself. So we have some of this going on in Berkeley in Sergey Levine's lab. And Laura Schultz, another developmental psychologist, has done some interesting work about this, about the idea that you might actually be setting goals for yourself. So actually kind of meta manipulating your reward function in the course of something like play. So one of the things that's really striking about kids' play is that they do, and again, this is something that you just talked about observationally, they'll do something for a while, and then they'll completely change their minds and do something else. And everything they're doing seems sort of random and silly. The example I always give of this is my grandson, Atticus, plays a game that we call Addy chess. And the way that you play Addy chess as opposed to regular chess is, for instance, you decide, okay, I'm going to take all the chess pieces and put them in the wastebasket. And then I'm going to take them out of the wastebasket and put them back on the board. Or I'm going to knock over all the black pieces, but not knock over all the white pieces. And you can watch him setting up these internal separate goals, none of which are kind of relevant goals to chess, and then figuring out how to accomplish them. And there's some interesting formal work that suggests that from an RL perspective, actually setting up goals, even if they aren't actually the goals that are going to lead to reward, and then enabling yourself to figure out what kinds of plans would lead to those goals, means that then when you actually are in a situation where you have reward, you have this kind of repertoire of strategies, of goal-directed strategies that you can call on. And again, this gets back to Deepak's point about those are the kinds of things that give you generalization, give you a wide range of different kinds of things to explore, as opposed to just the very specific skills that, say, people in machine learning have typically talked about.
Yes, I would basically like to, oh, I have feedback, I guess. I would like to comment on just one interpretation of the question. How do humans decide to interact with objects? As reading it as they decide to because they are told to, and they have been socialized, and they have learned to follow the rules. So I guess one thing that we have already been using in some of the research on embodied AI is language, communication between agents, or communication towards an agent that receives instructions. And I'm thinking of the work that Alex Schwing has presented about agents collaboratively solving a task and having to communicate among others, or also research on emergent communication between agents.
Yeah, so one thing that's come up with this is that humans seem to transfer quite well to novel situations, but AI, on the other hand, doesn't transfer very well. We have to use a fair number of tricks for that. Judy, based on the discussion that we've been having here about kids, I'm curious if you have anything that you want to add.
Yeah, it's an interesting discussion going on all about what form of supervision is being used in order to learn our models. And one thing that I'm curious about, and one thing that we've looked at recently, is in AI systems, in order to make sure that they can transfer later, you have to explicitly ask your rewards or your different supervisory signals to influence only subparts of the network. And if you don't do that, then everything gets kind of tangled together, and it can become more challenging and more data inefficient in order to transfer to new situations. So has there been any work in looking into that sort of behavior in people, some sort of isolation of computation, some sort of using or transferring different knowledge from certain circumstances to another, or subparts of the knowledge? I know there's been some work in RL on sub-goal learning, which is sort of a form of this, but explicitly within the learning system. So does anybody work on this or know of different ideas of how can we encourage this kind of transferability?
Yeah, Linda?
So I don't, of course, I don't have any computation solutions for you, okay? But maybe at the high level. But I actually think that the brain does two really interesting things, okay? It has a whole lot of different components that are kind of isolated from each other with built-up competencies, okay? But I think what stops them from overfitting and enables generalization and innovation is that they are all used in multiple tasks, okay? So whatever you have to do to recognize faces, you're also going to do to recognize objects and letters and tools, and it's going to be connecting to emotional stuff and to motivation stuff and to hand stuff for picking up. And there's just a lot of influences because everything's reused. Every part of the brain is reused multiple times. Different configurations with different tasks, writing letters, singing letters, reading letters, you know, they're all combining with different combinations of activities. And I think that's actually what loosens, stops the overfitting, helps find general principles that work across domains, and actually leads not just to generalization, but to innovation. Just a thought.
Judy?
Yeah, so we've definitely seen something similar with the need for multitask learning. And what you mentioned at the beginning of this session about some sort of implicit curriculum seems like it may end up being important, because if you learn to specialize a task initially, it can be sort of a bias to the system that can be really hard to unlearn.
One thing that Linda brought up in her talk is that kids seem to have an ability that's similar to meta-learning, where they're kind of learning to learn. Francie, do you have something you'd like to add on that?
Yeah, I was just thinking as we were talking about transferability that it's not just the skill that we can transfer, right? It's also all the other things that we learn. And one thing that I'm super excited about and look into is this notion that humans seem to learn also about how they made errors and how they correct for it, and then and that is being transferred to other skills. And so that's a notion of meta learning. To me, I condense this into loss functions because that's how we condense, you know, errors. So I look a lot at learning loss functions these days, and they seem to be transferable more easily to new tasks. So that might be just a completely orthogonal direction to look at.
Actually, I don't think it is orthogonal. I think it's sort of, I was going to add this onto mine, but not being what I just said earlier ahead of you, Franzi, but I think that, of course, we have, you might not do it in the model, but we have many loss functions, right? And I think they're in the same way, or objective functions, I don't know what level we want to think about, but they, of course, are also getting reused. The little networks that they live in the brain are getting reused. And I think that there's some kind of genius in there that if I was much more computationally sophisticated like you guys could find a solution to. But I really think it's an interesting path to think about, is generalizing the objective functions themselves or the loss functions.
So I'm just going to quickly respond, sorry. What I meant with orthogonal is that I think most of the research seems to focus on like transferring the skill itself. And I wanted to just say there is this other direction to look at where you can transfer other components of your learning system, like the loss function, right, that you learned.
Gotcha.
I just wanted to add to the point raised by Linda about curricular learning, that sometimes in a sometimes even to solve a complex task, when we train our agents using reinforcement learning, we have to resort to curriculum learning and start with something simpler. This is what we needed to do when we were training agents to navigate in Street View, in the street learn environment. It was the only way to essentially achieve some good performance by starting with local navigation first and then growing up the area. And curriculum learning has been used extensively by many of my colleagues at DeepMind, starting from Chris Summerfield, who was discussing the application of this, and then other research on building better and better agents, even at Atari tasks and more complex tasks. There is we basically now think in terms of curricula of tasks and schools for agents.
Deepak?
So I had a very small point to make. So about the loss function and meta learning kind of stuff. So one question I have is, do we think that our learning methods itself good enough that they can make use of information if we just tell them via correction feedback, like, oh, do this, do that? Because in some sense, the biggest successes we have seen in, at least particular to deep learning, or maybe in robotics, and Dieter can talk about that as well, is that putting in structure into the learning time itself seems to go a long way. Like convolution in a deep network leads to convolution in a network, and that structure, its learnable structure, helps quite a lot. Modularity, if you can put it at the word level, that helps language a lot. Maybe 3D, like Dieter's work has been doing, that helps innovation a lot. So of course, enforcing it via tasks is one way, but this other direction is to enforce it via learnable structures or some general idea that we have learning should capture, and we somehow put that into the network itself. I think Dieter or Linda, we can comment on it, but I think these are also, in my baby view of the world, I think this, so far, this putting structure had led to very strong progress on the machine learning side.
Maybe I can just briefly respond. Yeah, I totally agree that, of course, we need to come up with good structures that enable these networks to kind of learn with much less data, right? And incorporating somehow structures that support especially this reasoning in a three-dimensional world. And I think we're just at the beginning of this, right? The big question is, of course, how much you want to put in, right? And as roboticists, there might always be an approach coming maybe too strong from the model-based side, where we say, we're going to put in all the structure we know. Whereas on the other hand, of course, you might say, oh, we don't put any structure, right? And where you should be on that slider is just, I think, a totally open question. And I think, but that's, from my perspective, one of the most important ones.
Lynn, did you have something to add to that?
I don't want to dominate here, but you keep saying such interesting things. And I think that on this question of the structure, I think you also want to look in the structure of the data. So actually in another talk I'm giving at CVPR this afternoon, I'm going to say a little bit about these findings that we have. But one of the things that babies is that when they're objects, they actually biasly create 2D mass. This is even with occlusion or whatever, in which there's a strong height width ratio in which there's one axis of the 2D mask is elongated. And here's the kicker, okay? It is, not perfectly, but reliably and strongly biased to actually be the major axis of this object. So what that is for you, is I like long images of an object, they are actually lining up the longest axis on the retina with the longest axis of the object, which gives you just a pathway into building 3D, however you might do it. It might be similarity spaces, might be something fancy, whatever, but building some kind of a 3D representation of that object. And that gap between connecting the 2D image, which is what we have to start with to finding the 3D structure, that's a little tiny bias, do you know what I mean? But it's one I think that is extraordinarily powerful without having to say they're born with a three-dimensional object image. I mean, it's just going to be in the latent structure, given that bias. It solves a huge problem.
Franzi?
Oh, I'm unmuted. Okay, wait, I have to remember what I wanted to say. So I was reacting to Deepak, basically. And so I think, first of all, when you learn loss functions, it sounded like Deepak is wondering whether this is feasible, given, you know, that we have problems learning just normal skills. And it is feasible, so there is a lot of work on this, right? And the thing to not forget is that you can also put structure into a loss function that you're learning. And indeed, that's something we've done, and it seems way easier to learn these structured loss functions then. And still, they're more flexible than the standard loss functions that we use so far, right? So that's just something.
So I was just trying to be more controversial. So like your past work has put in the dynamics of structure into the learning process, and your current work is putting meta learning, statistical loss learning. So which one do you think, like, which is going to be more, maybe both, but I was just trying to be.
Similar to Dieter, I would say as a roboticist, I always try to use structure wherever I can, just also to make these real robot experiments feasible, right? But I don't know the answer to where the structure ends up being most useful. And so I'm exploring it in meta learning right now. And we'll see what happens.
Judy?
Springboarding off of this discussion of structure, and I forget who mentioned it earlier, but I do think that structure doesn't only need to be limited to how you design the architecture of a system, but definitely comes into play in terms of how you expose the system to different pieces of data and in what order. So of course, a curriculum in terms of a sequence of loss functions is one way, but even just in static learning, we make the choice to randomly shuffle our data. And if we don't do that, if we look at it in a sequential manner, the learning is very, very different. Now, when you have an embodied system and you have the ability to explore a space, just like Linda was saying, people perhaps have a particular bias in how they decide to explore the space. So it may not be a completely unstructured curiosity. There might be curiosity focused on a particular region of the space or a particular type of object to really try to understand that first before moving on.
Sonia?
Yeah, so this further springboarding, from all of these discussions, one thing that humans have very strongly is a focus of attention, right? That the world is very complicated. There's many, many actions we can perform at any one instance. And yet we see, you know, fairly rational behavior most of the time. Even in young children, we can sometimes watch and understand what they're doing. And so I was curious if anyone has any insights. I know it's been a major work, you know, and there's been great advances in terms of techniques for AI systems in terms of focus of attention in recent work. But from kind of a psychology standpoint, or maybe if anyone on the computational side has cool innovations that they want to highlight, you know, how does attention fit into this discussion of knowing what to do, when to do it, and learning from what you're doing?
Dieter, I see a hand from you.
Oh, I actually would like to first see an answer to Sonia's question.
Oh, okay.
So I'll defer.
Well, I think this kind of bootstrapping idea, which is connected to the curriculum, but it's a curriculum that's really sort of internally determined when you're looking at what children are doing, is very relevant to this question. I was going to mention it thinking about the modularity question before as well, which is attention kind of imposes modularity on a system. So attention is a way of just saying that you're only going to be considering a certain part of the system at a particular time. And the idea is that these, something like a curiosity-based motivational system has the effect of shifting the focus of attention that you have as you learn more. So this is a very old idea that there's this kind of zone of proximal development, as Vygotsky called it, where the things that are somewhat surprising, not things that you really understand extremely well, are the ones that capture your most attention, as opposed to the things that you really have, that you really understand extremely well, where you have a lot of structure, or the things that just seem to be completely random that you don't have any chance of extracting structure from. And I think we can see with the kids that they very often are sort of pursuing that zone of proximal development. So again, this is a very old idea in developmental psychology. If they understand something too well, then they're not interested, they're not going to explore it. If it's completely random, doesn't make any sense in terms of the structures they've already got, then they don't explore it. But in that intermediate space, that's where you actually see the most exploration, and that's where you see the most attention too. So you see attention being drawn to that space of things that are in between. I also wanted to mention something about what Deepak had said before about structure. So it's often perceived that there's a sort of choice between either building in a lot of structure in the first place as a way of having structure that allows inferences, which has the advantage that it constrains the search space, but has the disadvantage that it constrains the search space, or else having learning systems that are simply extracting what's there in the data and don't involve structure. So there's this kind of classic opposition, really going back to this is with my philosophy hat on, going back to Plato and Aristotle, between either views that say there's a lot of structure but not much learning, or else say there's a lot of learning but not much structure. And I think we can point to at least examples now where you see both. So for instance, in the case of causal inference, there's actually quite a lot of computational work, the kind of work that Judea Pearl did, and now work that's getting a new kind of revival in work that people like Yeshua Bengio are doing, where in the causal case, what you can see is that you look at a statistical pattern, you infer structure as a result of that pattern, then you can use the structure to do things like drive where it is that you should look next. So it's a kind of internal curriculum rather than a curriculum that's imposed from outside. And then as a result of getting the data, you can revise or modify the structure. So, you know, the old idea about children being developing intuitive theories, that's kind of how in theory formation works in science, where you take a bunch of data, you infer structure from the data, you use that structure to determine what your next set of experiments is going to be, what kinds of data you're going to pay attention to, what kinds of data you're going to ignore. That leads you to revise the structural representation you have, and so forth. But all of that is assuming that this reward function is this kind of epistemic, largely this epistemic reward function, rather than being a kind of utility-based reward function. And from the RL perspective, there's no reason why you can't have an epistemic reward function or an epistemic objective function or an epistemic loss function as well as you have a kind of classic utility-based score loss function. And I think it's very interesting to think about putting those two things together. So trying to think about what would an epistemic, a kind of epistemic reward function or an epistemic objective function look like, and how might that epistemic objective function change as you go out and you actually get more data about the world.
Go for it. Go for it.
I would like to apologize because I'm stepping back one question. There was a point raised by Judy, I believe, on sharpening the data, and that point also came up in several times. Also including in the talk by Linda about curriculum learning, etc. We don't have actually a good reason for shuffling the data, or we do it for the wrong reason, because we conflate the environment and the training algorithm. Before neural networks, convex optimization of superconductor machines assumed that you present a batch of data points to the optimizer, and then you get, and with a loss function, and then you fit the function to it. And it's only because Léon Boutou and Yann Lequin published papers on stochastic vision descent that this was adopted, rather than, let's say, using batch gradient descent with second order optimization. So that idea of shuffling the data and assuming that shuffling the data will solve everything from stability of a trainer to IID and stationarity of the data was essentially just a trick to get the optimization to work. And then the problem is that in reinforcement learning, even though reinforcement learning forces us to step away from shuffled data because the agent is following the curriculum of its own active learning, right? We still try to employ multiple agents, and so we shuffle data. We have batches of experience from different agents experiencing different parts of the world. But the only reason why we shuffle data is for the stability of gradient descent. But we could try to dissociate completely thinking of the experience of an agent, and you rely on episodic memory to store only a very partial exploration of the agent of the environment, and dissociate that from some algorithm to get the predictor to work. And if we start thinking in these terms, we can liberate ourselves from this shuffled data paradigm.
Judy?
Yeah, no, I completely agree. I think that the fact that we need to shuffle data is, at least to me, a sign that we're doing something a little bit flawed. And if you kind of dig into the math of what's happening with gradient descent and you look at those first few updates, you're there's no way around it. If you didn't shuffle data, you would be updating your model in such a way that it would be very, very hard to deviate from later. And so what happens is there's kind of this stochasticity and back and forth updates that can only happen because you are shuffling between different potential predictions, especially if you're using something like cross entropy loss. So there's sort of decisions that we're making at the loss function level that influence the type of data that we need to put into the system in order to learn the model. But all of that is adding structure to the weights that we end up learning. So I think it's important to think about structure at all different levels, both like how the loss, if we have multiple loss that are influencing at once, this kind of allows you to break this symmetry that you have from something like cross entropy. So that's one way to do it. But you might also want to just think about whether or not that's really the most efficient way to do the learning or the transferring to begin with.
Yeah, so I'm going to use this point to shift gears a little bit to a question from the poll. So moving beyond navigation, what are the next tasks and tools we as a community need? I'm particularly interested in Heidi's perspective on how do we build out the simulation infrastructure to enable a world where maybe we don't want to assume IID data.
Sorry, I guess I can jump into that. But do you mind rephrasing it? Because I think I missed some of the first part of it.
Yeah. So moving beyond navigation to other embodied AI tasks, what are the tasks and particularly the set of tools that we need to explore them? And how do we get to the scale necessary to do that? Because the reality of RL algorithms is that they're not nearly as simple as efficient as kids yet.
Yeah, so I think from our perspective and what we've been working on is, and I do have to quick disclaimer, I have a 2-year-old in the background, but what I kind of see, happening and going on is a cloud, obviously we need to, sorry, 1 second, is that we need to kind of get to a state where we can actually start to do a lot more development, not just locally, but obviously at cloud scale, especially with reinforcement learning. I think, what we've seen to date is, especially within industry, is, certain players in the space can get to cloud scale very quickly, but others don't have the availability, they don't have the infrastructure, they don't have the tools to be able to kind of help facilitate that, whether that's, researchers working on things, different problem sets, different universities, being able to get those tool sets and get up and running and doing so at something that's, you know, kind of within budget, which is always a hard thing to kind of meet as well. But also meeting developers kind of where they're at. So giving them the tool sets that they need that can kind of get them up and running quickly and iterating faster. So kind of creating experiments super quickly that can get you up at cloud scale is kind of an optimal thing so that, you know, you can kind of get the data that you need to feed back faster. So those are some of the challenges that we've been working on as far as helping developers get to that very quickly. So, you know, simple command line interfaces to be able to get up and running in simulation. On the simulator side, obviously, you know, there's robustness in certain sectors for being able to get, you know, simulators working within certain things, but I think there does need to be more work as far as making the simulators themselves more, you know, general scale to any sort of sector. So I think that's a lot of work that still needs to be done there, you know, and that's something that we're also exploring into as well and finding out. You know, from my perspective, there's different aspects of business that come into play as far as how those things are sustainable and whatnot. But I know that there's a lot of interest from the research perspective as well. So hugely interested in kind of learning from that perspective, where you guys are coming from.
Yeah, Alex?
Yeah, I think, I guess coming back to the question that you asked, you know, what are the next steps beyond navigation? I think one of the things that we need to is we kind of need to grow up. You know, much of this discussion here evolved around training RL agents and kind of mimicking or trying to make them similar to how kids learn. But, you know, kind of speaking about growing up, once we grow older, we start to collaborate. And, you know, it's not one person running or solving a particular task. You're learning to solve tasks collaboratively, you know, working together jointly as teams. And I think that is one of the topics that doesn't or hasn't received a lot of attention, you know, just yet. How can we solve tasks collaboratively? How can we train agents to collaboratively solve tasks? How can they develop strategies to solve tasks? I think that is a big open field where there also has to be some support from development of, you know, infrastructure in the first place. There's, you know, there is a few right now environments that support training of multiple agents, but I think there's still a lot of research needed, particularly in that direction, in order to really help us grow up and make this a really embodied environment, so to speak. Personal opinion.
Thank you.
Yeah, that's great feedback as well. And most of the tools that we've been working on in that space are only, you know, single agent to simulator. And so I think that is, even from our perspective, you know, kind of, it's a big challenge in and of itself. So taking that on, you know, I think is definitely helpful on all sides.
Piotr?
I would like to disagree with the first few words of the question, moving beyond navigation. I would say that it's premature to do so, simply because navigation in larger environments or in changing environments, or navigation as we solve it as humans, let's say once the lockdown is finished, we will be traveling places and relying on maps and asking for directions to various people that we meet on the street. So navigation is essentially can be seen as a relatively high cognitive task, and Yoshua Bengio used the example of an agent being able to go to a city that it never visited before and achieve zero shot or one shot perfect navigation just by using some symbolic representations from maps and asking for directions. So that means that the tools that we need to consider would be multi-agent, collaborative mapping, or communicating agents using language. And yeah, I guess there is the platform that Heidi has been discussing, or Alex that mentioned, and the tasks that Alex had been working on are interesting navigation tasks, because tasks that rely on going very far away to a completely unseen area and having to rely on other agents to communicate some description of a place.
Dieter, you seemed like you had something you wanted to say.
Yeah, so I agree that navigation is important, but I disagree that this is where we should stay for a while, because I think I'm a fan of looking more into, for example, active manipulation kind of tasks, because I think navigation focuses very much about, of course, the large scale spatial reasoning, but at the same time, I think what it ignores is really this close-up physical interaction, right? Where you're seeking contact with your environment, and through this contact, you're learning spatial representations that I think for navigation tasks, mostly you don't really need. At the same time, I think the simulators are getting better and better. So I think we should actually be at the able now to learn reasonably interesting manipulation kind of tasks that then, coming from a robotics perspective, we can actually transfer to the real world. So it's not like we can only do these things in simulation, but I think we're getting better and better at that. The question, what kind of tasks we would want to look at, is of course important, right? I don't think we are ready for, let's say, washing dishes in the sink or things like that, which is some of the tasks that, of course, some of the simulation environments are looking at as part of these environments. I think these are interesting if you really care about language grounding and these higher level reasoning tasks. So I think it's totally valid to look at that. If you want to look at tasks that have a higher chance of actually succeeding on a real robot, I think for now we might stick mostly with pick and place, open close cabinets and drawers. I think we're pretty close to actually being able to execute these in the real world. And I think those still ask interesting questions.
Yeah, okay, well, we are pretty much at time. I see Deepak has a hand raised though.
Sorry, I had an inkling for a point which was raised much earlier in the talk, and the point was about data shuffling, and the culprit we found was SGD. But I think there is a bigger culprit out there which we did not address in the room, like elephant in the room. I think the culprit is relying on the data being IID. Like we just want the data to be IID or identically sampled from everywhere. And whichever problem we kind of try to address, we try to mold it into that mode. Like for instance, in navigation, there are a lot of work where you try to collect a lot of passive data for navigation and then try to learn it as if it's IID data, right? And one of the challenges in embodied agents is to be able to move to this non-IID setting and learn as effectively as we did in the IID setups, like ImageNet or something like that. And I think that's one of the fundamental challenges which I don't know the answer to, but if anyone else has a comment on this.
I just want to add one thing to that, which is to say that I agree completely. When the data does not come in an IID fashion, it breaks the current learning protocols. But to me, that's an issue with the way that we're learning. We should be able to learn from sequential data. We should especially be able to transfer or learn specializations for a subset of our loss functions on sequential data without it negatively impacting the things that we used to know how to do. And so whether or not isolation of computation will help with that, or changing away from SGD, or changing out our loss functions, or adding low-level structure, I think all should be explored as potential solutions.
Okay, so we have one final kind of question to begin wrapping things up on. We are at time, so if you do need to go, that is of course perfectly fine. The one final thing is, I want to go around through everybody once again and have everybody give what they think the big takeaway from their talk or their line of work should be for this audience. So let's start with, once again, we'll start with Alex. All
right, I guess 1 minute summary. The one topic as I kind of push for towards the end of the discussion as well that I'm personally very excited about is at this point in time, multi-agent learning. How can multiple agents learn to collaborate, to communicate in order to jointly solve a task, as opposed to just having single agents that navigate towards certain goals or achieve certain tasks. So really the development or learning of strategies for multiple agents is the one thing that we are trying to pursue at this point in time. Thank you.
Alison? Alison, you're muted currently.
Yeah, because I actually wanted to respond to that point. One of the things that we know about babies and children is that they're not actually at all just individuals going off and trying to explore by themselves. And one of the things that we're doing is looking at all the many kinds of social learning that children are engaged in. And in fact, you could argue that children are more engaged in multi-agent learning than even adults are. They're always paying attention to the information that they're getting through imitation, through testimony from other people. And we're starting to try to get some modeling that would understand that, although that's another talk. But I think in terms of the work that we're doing at the moment, this idea about trying to have an intrinsic motivational system, a kind of intrinsic epistemic motivational system, including things like curiosity, as opposed to thinking in terms of an external set of goal-directed rewards, and the advantages that gives you in terms of building a kind of intrinsic curriculum and getting generalization and transfer. I think that would be the big takeaway.
Oh, forgot to unmute myself, Deepak.
Hi. So my talk for this workshop was in fact about what does it mean to design pre-training for robots. Because in deep learning, one of the biggest successes is in the fact that once we train the network, it transfers really well to different tasks. But what does it mean to transfer for a robot? Because every robot can be different. My robot may have 2 legs, your robot might have 1 leg or 2 hands. And what does it also mean to pre-train a robot on, like, what do I pre-train on? Do I pre-train on picking, pushing, grasping? And so my talk tries to shed some light for these 2 questions. For the first question of how do we transfer across robot, we propose modularity across motors of the robot as a solution, as a potential solution. The results are still very early on. And for the second question of which task to pre-train on, I discuss maybe it's a good idea to pre-train without any task knowledge. And by task, I mean extrinsic task. So when Linda says intrinsic task, I count them in the non-task. I count them in the exploration phase. So without the knowledge of extrinsic tasks. So these 2 questions are summarized in the talk.
Peter?
Yeah, in my talk, I looked at kind of visual navigation and robot manipulation kind of settings from a roboticist perspective, and looked at these different kind of environments that are being investigated by the embodied AI community. And with respect to visual navigation, I actually feel like that many of these results nowadays can transfer to real robots, where we can start to learn full navigation systems that actually work when they are trained in environments like Gibson, for example. And then with respect to manipulation, I'm also actually positive in the sense that the gap is not as wide as you might have thought, let's say 5 years ago or so. So nowadays, I think when it comes to picking up objects, opening drawers and closing drawers and cabinets, which are some of the tasks that people look at in these environments, I think actually we can get pretty close to executing them on a real robot. And the only assumption we need to make is more or less that you can detect the object that you want to pick up, or you can segment it out in 3D. You do not need to necessarily recognize the exact shape of the object, right? We can do this with depth cameras then. And I think that's actually a pretty good development, that we're getting closer to bridging that gap, also by growing capabilities from the robotics community that make it closer to the simulated setting. Of course, the gap to things like washing dishes and things like that is still too wide, but I think we just gotta keep on working on that.
Franzi?
Yeah, my talk was about learning loss function for robot tasks that involve dynamics. And, we actually look at the pick and place task where it seems infeasible to learn how to correct for each object, because each object, you might not even be able to observe the mass and things like that of the object. So instead we look at learning how to correct for errors that are being made, that you're sensing as you're picking and placing. And the two key takeaways are that learning the loss function actually outperforms a standard like mean squared error loss function on a pick and place task, even though we didn't train on a pick and place task. And so that was the second kind of key takeaway, that the meta train distribution was completely different from the meta test scenario. And we did see this generalization, and that is pretty exciting.
Heidi?
Sure. So my takeaway, I guess, in my talk as well, is about democratizing the tools as well as development lifecycle and QA. And, I think from here, obviously, like getting multi-agent environments for collaboration. We work in autonomous vehicles now, so as well as just interaction up and running and doing so successfully, for both engineers and industry as well as other stakeholders. I apologize, I live in a New York City apartment. It's hard to get away from anything. So 2 dogs and a kid. So those are kind of my key takeaways, is how to help enable others to develop faster, but also safer. So some of the things that we're working on too is around the data and trying to get data in the hands of developers without them having to actually do it. So especially within simulation, it doesn't, it's not quite the core problem set that you guys are working on. So helping to kind of gather that data and get it to you is where we're trying to help make those ends meet.
Judy?
Yeah, so my talk for this workshop was thinking about how to learn representations that are more transferable, both to different tasks, but to also different visual environments. And 2 of the things that I was looking at was ways in which you can introduce different forms of modularity or structure into your learning systems, as well as ways in which you can manipulate both the input data and the output losses, oftentimes as a result of manipulating the input data, but really with the core goal of finding different ways to encourage data efficient transfer down the road.
Linda?
So I think the major thing that I would like people to think about is really the structure of the data, in that in certainly human learning and human everyday life, we are deeply constrained by time and space to sample the world incrementally with a lot of repeated experiences with things that are physically near us. We don't jump around the world or jump from item to item. It is not a random assortment. And I think there are deep principles in the way we experience the world, in really the statistical structure of the data, that are going to be generalizable to even other problems, to problems how you rapidly, for example, can learn to generalize from very few bad examples. And that we just need to think deeper about the data itself, okay? And because it's half the problem.
Piotr?
So my takeaway from the panel is that it would help for agents if they could play and manipulate the environment, interact this way with the environment. So manipulation is probably manipulation, and various forms of exploration, curiosity, or key components for embodied AI. And but my talk was about navigation only, and it was entitled "Still Learning to Navigate." I was basically reflecting in a critical way about some of the work I've done and some other colleagues have done in that field. For instance, looking at inductive biases, taking from neuroscience about grid cells, or curriculum learning to make tasks tractable. And so the whole idea of being able to learn presentations in an implicit way in agents, and then try to overcome the limitations of those agents via two approaches. One, which is to ground presentations of space with language, or ground language in presentations of space. And the other one was essentially try to address other issues of generalization to new environments. And
so,
for
yeah.
that, yeah.
Oh, sorry.
And for that, relying on fast memory, episodic memory.
Okay, now in Sonia.
All right. So in my talk, I talked about two things. One is center-real transfer and developing a metric that can help predict performance. And so center-real transfer and help us develop simulators or characteristics of simulations that facilitate the transfer more accurately, or enable us to predict performance in the real world more accurately. And then the other thing I talked about is semantic grasping and how incorporating a wide range of contexts, including what you're using the object for, and whether it's clean or dirty, what its state is, is it hot, what are you going to do with it, and how that can help robots determine how to actually interact with the world better, and so that they can grasp objects more reasonably. But for my summary, real quick, I actually want to address one of the questions that came up in the poll that is dear to my heart. It's about tabula rasa learning and whether we should always be, how much should we learn from scratch and how much should we bring data with us when we learn. I spent many years, I think, focusing on experiments where everything was being learned from scratch, as many of us do. That's the simplest type of experiment. At the same time, there's a lot of work on transfer learning and generalizability that way, as others have already mentioned. But increasingly, I'm really interested in how do you bring semantic knowledge, abstract knowledge, general knowledge with you, and really try to avoid complete tabula rasa learning, because it feels artificial. It feels like that's not how humans operate, right? What makes us efficient learners is that we have a lot of history that we're bringing with us, and a lot of shortcuts, and a lot of things that help us focus on just the right things. And to me, this is a really, really interesting future research direction. Current research direction is how do we continue to improve our models in terms of their ability, not just to transfer something that they learn to another embodiment or to another task, but really to bring in abstract knowledge to help drive some of the low-level knowledge. So that's for me.
Yeah, thank you very much. Well, thank you to all of our panelists. This has been recorded and will be online, and also obviously all of the panelists have talks that are available online, and there are more talks from others who couldn't join us for the panel today. So thank you to all of the panelists once again.
Thank you.
Thank you.
Thank you.
Thanks for organizing.
Thank you.
Thank you.
A pleasure.